In this video, let's go over the problem titled Count Subarrays with Sum K. We'll go over what the problem is, an example, and then I'll go over first an inefficient solution followed by a better solution. Let's start with the problem description and run through an example. The problem description is given an array and value k, count the number of subarrays that sum to k. So implicitly, we know that this array will consist of numbers, so it'll be integers, and k will also be an integer. Let's look at an example. We have the array 1, 0, -1, 1, and we have k equals 0. So let's see which subarrays sum to 0, and I chose one that's size 4, so it's easy to look at by eye. So let's start from the beginning. We know that 0 as a single element will sum to 0, so that's one subarray. Then we have that -1 plus 1 also equals 0. That's two subarrays. And finally, we know that 0 plus 0 equals 0. So 0, -1, and 1 should equal 0. And the last one that we have is 1, 0, -1. That's also actually equal to 0. 1 plus 0 is 1, minus 1 is 0. And I think we covered it. It's a little hard to tell, but we have 4 different subarrays that sum to 0. Now, notice that we didn't actually say continuous subarrays in the problem description, but that's an implicit assumption. Make sure you clear that up with your interviewer because those are two different problems. So we have 4 different subarrays that sum to 0, so we'll return 4. And that sums it up. So that wasn't a super intuitive solution. It was kind of random. I went all over the place and it didn't seem super obvious how we could translate this into an algorithm. So because of that, let's just try to brute force it and come up with a very bad algorithm that at least kind of works. Now, there's a very obvious bad algorithm, and then there's a little less obvious but still pretty obvious algorithm that we'll use. The first one that I won't actually code up is just if we checked every single subarray. Now, that's a very brute force algorithm, and we could just look at every subarray, sum the values, and see if they sum to k. If they do, we would just increase our count. However, that runtime is pretty bad. It'd be n cubed. N cubed is a very uncommon runtime as is, so if that was our final runtime, it probably wouldn't be that great. So let's see if we can think of an n squared runtime instead. Now, looking at this array, I know that we're looking for subarray sums. One context piece that I have in my mind is that when we're doing the sum of a subarray, it's often useful to think of things in terms of the cumulative sum. Let's write down the cumulative sum array for this array. So to go over what that means, I'll write it out without actually adding the numbers. That's our cumulative sum array without adding the numbers. So you'll see the first element is our first original element. Our second element is the first element plus the second element. Our third element is the first plus second plus third element. And our last element is all the elements in the array combined. And if we add all those numbers up, this is what we get. And there we have it. Our cumulative sum array is 1, 1, 0, 1. So I inserted this piece of intuition that the cumulative sum might be useful. But why? Let's take a look at our original array. Let's say that we wanted to figure out the subarray sum for these two elements. Now, of course, it's 2 elements and it's fairly easy, but let's just say that it wasn't so obvious and it was bigger. And for this example, let's think about it. What can we do to figure out those 2 elements' sum, or any number of elements, without doing much work using the cumulative sum array? So if we have this cumulative sum, that means that we know the sum from the beginning all the way to the end. We know this. So this is the sum of all numbers, and that's the last element in our array. Then we also know the sum from the first to the second value, right? So we know this value because this is going to be cumulative sum 2. It's cumulative sum of 1, I guess, because it's the second value. And we know those 2 numbers. Then we can take the whole sum. So we can take this one right here. We can subtract the sum at 1. And then we'll have the sum of the 2 elements after that. So we're basically starting with this whole thing, and then we're saying, okay, let's just take out these 2 numbers and see what's left over, and that'll give us the sum of the subarray we're looking for. Basically, we're able to calculate the sum of a subarray without having to sum up the elements over and over again. We only have to sum them up once in that cumulative sum array, and then we can check every subarray. So instead of n cubed, we should get somewhere around the magnitude of n squared, based off of, again, previous experience. However, I'm going to write this code out for you and prove to you that this is an inefficient still, but decent algorithm for this problem. Here's our function header. It's count subarrays. It takes an array, which is a list of numbers, and a value k. Make sure to go over this with your interviewer. The first thing we'll do is generate our cumulative sum array. Here is an empty array, and we've called it sums. That will store our cumulative sums. To populate this sums array, we'll start by adding our initial value. So for example, we'll have array of 0 in the first one, and then in our second index, we'll just take the array of the previous one, and we'll add our current index. And we'll do this over and over again. So for this one, the array of previous, this is referencing sums, and this one over here is actually talking about array. So basically we can build up our cumulative sum array element by element using the most recent value. We'll start by appending our array's initial value. An assumption I'm making here is that array is not none and that it's not empty or null. This is probably a fair assumption. This problem is complicated enough. We don't need to add that in, but discuss that edge case with your interviewer in an interview. So I've added the first value in array to sums. Now let's iterate over all of the remaining values and use the formula on the right side to generate our cumulative sums. So for all of our elements starting from the second one at index 1 onwards to the length of the array, we'll append the most recent value in our cumulative sum added with our current value in our array. And there we have it. So again, we're taking the most recent sum and adding our current value to it to build up this cumulative sum, as we did in the example and in the formula to the right. We now have our cumulative sums stored in our sums array. What we need to do now is essentially go over every single subarray and figure out if their sum is equal to k. So to go over each subarray, we'll just use a nested for loop, which is pretty standard. And because it's a nested for loop, this is where the n squared will come from, which we'll go over later in our time and space complexity. So let's create the outer loop from 0 to the length of array. So for each start index in the range 0 to the length of array, and for each n in the range start to the length of array. So the reason n can equal start is because we remove the value in our start. And let me show you what this means. Here's an example I've drawn up. We have the same array as before, 1, 0, negative 1, 1. We're looking at 0, which is index 1, and we're at the case where start equals end equals 1. So in this case, we want to still get the value at 1, and so we'll take our sums of 1 minus sums of 0. And what we've done here is we've subtracted 1 from our start value, and that should be how we generate the value for a single value array. So if it's a one value array, we still want that to be possible. And to do that, we'll say start equals end. Now, notice what we did here. In this case, we did start minus 1, which means that when start equals 0, start minus 1 will be negative 1, which will not give us the answer we want. So we'll just check for that in our for loops and make sure we account for it. Now we have a loop for each start and end. We're going to count the number of subarrays, but we never actually made a count variable. Let's make that now. We'll make that right before the outer for loop. Now count equals 0. So in our inner for loop, we first have to calculate the subarray sum. So there's two cases. Either start is 0, in which case we just use sums of end, and otherwise we'll say sums of end minus sums of start minus 1. So remember, our two cases are that we either use sums of end or sums of end minus sums of start minus 1, and we'll only subtract when start isn't 0. So to do that, let's just assume that start is 0 by saying that our temp sum is sums of end. And if our start is not equal to 0, we'll just subtract sums of start minus 1. So if start is not 0, then we'll subtract sums of start minus 1 from our temp sum. This just handles the case with start is 0, because otherwise it's tedious to handle. Now we'll check if temp sum is equal to k. I'm going to reduce the size of the code a little bit, but I assure you it's the same code. So if temp sum equals k, then we'll just increment count. And that's it. So we'll go over each subarray, every start and end in our ranges, and we'll make sure that we calculate the sum. We'll make sure to calculate it just in case we have the case where start is 0 and start isn't. So we'll subtract sums of start minus 1 if start is not 0. And finally, we'll just check if temp sum is equal to k, which is the value we were looking for. And we'll increment count. At the end, we'll return count. And that's a good brute force style way to solve this problem. Notice that we still use a cumulative sum array, which is a good intuition for subarray sum problems, and we end up getting an okay runtime, which we'll go over right now. Let's go over the time and space complexity. N will be the number of elements in our array. So for time complexity, we have this loop over here which generates the cumulative sums. It goes over every element once, so it's linear in time. And then we have these two for loops, which will be our bane. We have an O of n outside and O of n inside, and then everything inside is just constant time. So we have like addition, subtraction, and just if statements. So we have a time complexity of O of n squared. Then our space complexity has to do with the sums array. So our sums array is the only space we use, and it will be exactly the size of our array, which will be O of n. So our space complexity is linear, which is big O of n. So what have we learned here? We've learned that we can come up with a decent solution to what's otherwise a challenging problem by using two things, which is the brute force heuristic that we can just check every subarray, combined with the intuition that cumulative sums are often helpful with working with subarray sums. However, we haven't tackled how to solve this problem fully efficiently. So let's go over a solution that you may not get in an interview, but you might get close to, and this solution has to do with maps. This approach is a little more abstract, so let's start it off as such. First, let's talk about what it means when the cumulative sum at two places in an array are exactly the same. So let's say sums of I is equal to sums of j, and for simplicity, we'll say I is less than j. That means that the sum of the elements between I and j has to be 0, aka sums of j minus sums of I is equal to 0. So to think about this intuitively, let's just say that we're at some arbitrary value, and this is sums of I, where it equals k, and k is another value. Then we could have, like, let's say 1, 3, -4, and then sums of j. In this case, what I've written out, 1 plus 3 plus -4 is equal to 0. So sums of I equals sums of j. There is no other set of numbers. Of course, we could use other numbers there, but there's no other sum in between those two numbers that would work besides 0. Because let's say that instead of 3, we had 2. So our sum in the middle was -1. Well, then this sums of j would be equal to sums of I minus 1. So to say that the sums of I equals sums of j means that their difference must be 0. What does this mean for us? So before we check that sums of j minus sums of I equals 0, what if we change that to sums of j minus sums of I equals k? Well, then that would mean that the subarray from I to j has a sum equal to k, because there's a difference of k between those two sums. This sounds confusing. Let's wrap our heads around this by running a real example. So here's our sample example. 3, 7, -4, -2, 1, and 5 is our array, and our target value is k. We want to see how many subarrays sub up to be k. So here's what we'll do. We'll start from the beginning and create a cumulative sum variable. We'll call it sum. So sum will be equal to 0. We'll add the first number to it. So at this iteration, which is the first number, sum is equal to 3. Now we want to check how many times this value has appeared. So we'll say 3 minus 3, so our sum minus k is equal to 0. How many times have we seen 0 before? Well, we haven't had any way to store this yet. However, we're doing a lookup, right? So we're just doing a quick lookup. Have we seen an integer, and how many times have we seen it? So let's store this in a map. So let's say that we have some map structure. We look up sum minus k, which is equal to 0. And because 0 is essentially equal to the empty subarray, we'll have a default value that we've always seen 0 at least once. So we'll initialize our map by saying that 0 has 1. Now we'll see sum minus k is equal to 0. We'll look that up in our map and say, okay, well, we've seen 0 one time so far. So let's say now that we've seen 3 also one time, so that we can keep track of this later. And we'll move on, so on and so forth. We'll come here and sum will be equal to 10. So when sum is equal to 10, we'll say, okay, we're looking for 3. So to look for 3, let's subtract 3 from our sum, and we'll get 7. And have we seen a 7 before? No, we haven't seen a 7 before, but we have seen a 10 now. So we have a subarray that sums to 10. That's one of our cumulative sums. So let's just say that we've seen 10 here once. Now we're at this value. So we'll say 10 minus 4, which is equal to 6. 6 is our new sum, so we'll subtract away the k. We're, again, looking to see, have we seen the matching pair for it? Have we seen that sums of I previously for it? So we'll say 6 minus 3, that's equal to 3. Have we seen that before? Yeah, we have seen 3 before. We've seen it one time. So we'll add 1 to some count variable for the number of times we've seen k, and then we'll say, hey, we've seen 6 once in our map. We'll move on. Then sum is equal to 4 at -2. That's an arrow. It's very badly drawn. And what we'll say is, again, 4 minus 3. So we'll subtract k. So we'll say 4 minus 3 is 1. Have we seen a subarray that equals 1? So that means the difference between the subarray's index and its current index would be 3. Have we seen a subarray that sums to 1? No, we haven't. But let's write down that we saw a subarray that sums to 4. Then we'll move our sum over and say, okay, the next one is equal to 5, right? So 4 plus 1 is 5. 5 minus 3 is 2. Have we seen a subarray that sums to 2? So if we've seen a subarray like somewhere over here that equals 2, then that means that the difference between that value, let's say index I, and this index, which is j, sum to 3. Well, no, we haven't seen a 2 yet, but we've seen a 5 now, so let's update it. And I've added that into our map. And finally, we'll go to our last value, where sum will be equal to 10. So when sum is equal to 10, we'll subtract 3 from it, and we'll say, have we seen a 7? Well, we've seen a single 7, but that subarray from 7 to here, that won't sum to 3, and the reason is that the subarray up to 7 sum to 10. But we'll say, okay, let's keep updating our map. Have we seen a 10 so far? Wait, we have. And because we've seen a 10 so far, we'll cross it out and update it to be 2. So we'll keep track of how many subarrays we've seen prior that equal to each value. Now, having gone over this, I'm hoping it makes a lot more sense. We're essentially finding the earlier subarrays that have certain sums, and then we're updating our cumulative sum and looking for the difference with k and seeing if we've seen subarrays previously that have that cumulative sum. And the property we're using is this one right here, sums of j minus sums of I equals k. When we find those, we found a match, and we'll update a count. Let's put this into code. First, let's make a map, and we'll call it map for continuity's sake. Now, let's also make a sum variable for our cumulative sum. And I didn't write it explicitly, but we'll also need a count variable to keep track of how many times we've seen k. Before I continue, I want to go over this map. So it's going to be key value pairs. It's going to be a sum that'll map to the number of times we've seen that sum. So number of times we've seen it. And we'll update this map. Basically, we just want to make sure that we're keeping track of how many times we've seen a sum in the past, because let's say we've seen 20 5 times in the past and we get to a value that needs 20 to complete it to get to k. Well, we want to count all 5 of those previous subarrays, so we'll keep track of the successive ones. Then we have our map, our sum, and our count. Remember how we initialized our map in the last example? Our first value was 3 and k was 3. And 3 minus 3 is equal to 0. So we want to make sure that we always have at least one count for 0. Essentially, if we have a 0, then we have a cumulative sum that is exactly equal to k, so it's from the first element up to whatever element we're at, and in that case, we should count that occurrence. Now, after we've done all this, let's start iterating over our array. So for each index in the range 0 to the length of our array, we'll first update our cumulative sum. Let's check if we've seen sum minus k in our map. So have we seen the correct matching pair for our sum to come up with the value k? So if sum minus k is in the map, then let's get the value and make sure that we update our count with it. So count plus equals map of sum minus k. I'm writing this in Python, but I advise you to be familiar with how to do this in your language of choice, whatever's comfortable. And otherwise, if it's not in the map, then that's okay. We'll just make sure to update our map with our sum's value. There's 2 cases, either our sum is already in the map or it's not. So let's just write an if statement for that. So if our sum is in the map, then let's just increase its occurrences by 1. And otherwise, let's set its occurrences to 1 because it's the first time we've come across this sum. So it's an else statement. And that just about wraps up our code. We'll make sure to return count at the end. And that wraps up our algorithm. So in this algorithm, we've used kind of a confusing concept, which is this cumulative sum property that if the sum from a later index minus the sum from an earlier index equals some value, then the subarray between equals that value. However, it's not complicated. I would guess that about half or maybe a third of interviewees get this solution in an interview setting, and it's especially challenging because there's a lot of stress on you to get an efficient solution. So if you're in an interview and you happen to get this kind of question, remember that cumulative sums can be helpful. Of course, run this by your interviewer. They might nudge you in the better or right direction. Before we end, let's talk about time and space complexity. Let's start with our time complexity. We basically have this for loop, and we have these lookups, which are constant time thanks to the property that it's a map. And therefore, our time complexity is linear, so it's O of n, and this beats our earlier O of n squared algorithm. And finally, our space complexity has to do with this map, right? So our map can potentially hold a bunch of different values, so it'll be O of n, linear in the size of our input, which means our space complexity is O of n. And that's all there is to it. I hope that you're a little more comfortable with using the cumulative sum arrays and solving problems like this, where you have to find the number of subarrays where you have a sum of some value.